Welcome to today's session. In this video, we'll dive into problem number 328, titled Odd-Even Linked List. This problem is a great test of your ability to manipulate linked lists while maintaining efficient time and space complexity. Let's get started. In this problem, you're given the head of a singly linked list, and your goal is to rearrange the nodes so that all the nodes at odd indices are grouped together, followed by all the nodes at even indices. Once reordered, you return the head of this modified list. Importantly, the relative order of nodes within both the odd and even groups must remain the same as their original positions in the input list. To solve this, your solution must operate with an O(n) time complexity and use only O(1) space, meaning you should work in place without creating additional data structures. Also, take note that the indexing here is 1-based, so the first node is considered odd, the second is even, and so on. The input is provided as the head of a singly linked list, where each node contains a value and a pointer to the next node. For the output, you need to return the reordered linked list, starting with all odd index nodes followed by all even index nodes. Let's go through some examples to understand this better. In the first example, the input list is 1, 2, 3, 4, 5. Here, the nodes at odd indices are 1, 3, and 5, while the nodes at even indices are 2 and 4. When we reorder the list, the odd index nodes come first, followed by the even index nodes, giving us 1, 3, 5, 2, 4. In the second example, the input list is 2, 1, 3, 5, 6, 4, 7. The odd index nodes are 2, 3, 6, and 7, while the even index nodes are 1, 5, and 4. Reordering these groups results in 2, 3, 6, 7, 1, 5, 4. Notice how in both cases, the relative order within the odd and even groups remains the same as in the input list. This is a key requirement of the problem. Now, for the third example, the input list is empty, represented as. Since there are no nodes to rearrange, the output is also an empty list. Looking at the constraints, the number of nodes in the linked list can range from 0 to 10,000, and the values in the nodes can range from -1 million to 1 million. Some edge cases to consider include an empty input list, a list with only 1 or 2 nodes, lists where node values are not unique, and cases where the list contains the maximum number of nodes or extreme values. Your solution must handle all these scenarios efficiently while staying within the problem's constraints. To tackle the problem of rearranging a linked list into odd and even index nodes, one approach we can consider is a brute force method. The idea here is to create two separate lists, one for odd index nodes and another for even index nodes. As we traverse the input linked list, we alternate between adding nodes to these two lists based on their position. Once all the nodes are processed, we simply merge the two lists together, starting with the odd list followed by the even list. This approach is straightforward and easy to understand. In terms of implementation, we would first initialize two dummy head nodes to keep track of the odd and even lists. Then, as we iterate through the input list, we maintain an index counter to determine whether the current node should go to the odd or even list. Finally, we make sure to connect the two lists. While this method has a time complexity of O(n), because we only traverse the list once, the space complexity can vary. If we use explicit additional lists, the space complexity becomes O(n), but if we link nodes directly using pointers, it reduces to O(1). However, the trade-offs include cumbersome bookkeeping for reconnecting nodes and the additional space overhead, which makes this method less efficient in practice. A more efficient solution is the optimized in-place approach, which eliminates the need for separate lists altogether by rearranging the pointers of the input linked list directly. The intuition here is to maintain two pointers, one for odd index nodes and another for even index nodes. These pointers traverse the list simultaneously while restructuring the connections between nodes. A key observation is that odd index nodes should only connect to other odd index nodes, and even index nodes should connect exclusively to other even index nodes. To make this possible, we need to keep track of the first node in the even group, as it will be appended to the tail of the odd group at the end. To implement this, we initialize two pointers, odd and even, starting at the head of the list and the second node, respectively. Additionally, we store a reference to the even_head so we can easily reconnect it later. As we iterate through the list, we update the odd pointer to skip over the next even node and instead link to the following odd node. Similarly, the even pointer skips over the next odd node to link to the following even node. Once all nodes are processed, we simply append the even underscore head to the tail of the odd list. This method processes each node exactly once, achieving a time complexity of O(n), and because it doesn't rely on auxiliary structures, the space complexity is O(1). This optimized in-place approach is highly efficient, with a time complexity of O(n) for a single traversal and a space complexity of O(1), since no additional storage is required. The trade-offs of this method include slightly more intricate pointer manipulation compared to the brute force approach, but the benefits far outweigh the challenges. It is efficient in both time and space, making it the preferred strategy for this problem. By restructuring the pointers within the existing linked list, we avoid the overhead of creating new data structures, which is especially advantageous for large input sizes. Additionally, this approach adheres to the problem's constraints by maintaining the relative order of nodes within the odd and even groups. This strategy demonstrates the power of pointer manipulation in solving linked list problems efficiently. While the brute force approach offers simplicity in conceptualization, its redundant operations and extra space usage make it less appealing. The in-place method strikes an ideal balance between clarity and performance, making it the optimal solution for this problem. In this problem, we aim to reorganize a singly linked list by separating its nodes into two new lists based on their indices. Here, the indices are one-based, meaning the first node is odd-indexed, the second is even-indexed, and so on. The odd-indexed nodes will form one list, while the even-indexed nodes will form another. To achieve this, we start by validating the input. If the input list is empty, we simply return null for both lists since there's nothing to process. After that, we initialize two dummy nodes, odd_dummy and even_dummy, to serve as the heads of the odd and even lists. These dummy nodes help simplify the process of adding nodes to the new lists. We also use two pointers, odd and even, starting at the dummy nodes, to build the lists dynamically. Additionally, we set up a current pointer to traverse the original list and a counter, index, to keep track of the current node's position in the list. Now, we traverse the input list using a loop that continues as long as the current pointer is not null. At each step, we check whether the current index is odd or even. If the index is odd, we link the odd pointer to the current node and move the odd pointer forward to the next available position. If the index is even, we link the even pointer to the current node and move the even pointer forward. After processing the current node, we increment the index counter and move the current pointer to the next node in the original list. Once the traversal is complete, we ensure that both the odd and even lists are properly terminated by setting odd.next and even.next to null. This prevents any potential cycles or dangling references. Finally, we return the next pointers of odd_dummy and even_dummy, which represent the heads of the completed odd-indexed and even-indexed lists. To make this algorithm efficient and easy to implement, we leverage a few key techniques. First, dummy nodes are used for both the odd and even lists. These provide a fixed starting point, eliminating the need for special handling when adding the first node to either list. Second, we use a counter to track the index of each node as we traverse the list. This ensures that nodes are assigned to the correct list odd or even based on their positions. Third, by updating the odd and even pointers immediately after adding a node, we ensure that the new nodes are appended correctly without overwriting existing connections. The algorithm relies on singly linked lists for their simplicity and efficiency in traversal, and pointers like current, odd, and even are used to maintain O(n) time complexity. Additionally, the space complexity remains O(1), since we only use a constant amount of extra memory for pointers and counters. When implementing this algorithm, it is important to account for edge cases. For example, if the input list is empty, the algorithm should return empty odd and even lists as there are no nodes to process. In the case of a single node list, that single node will belong to the odd indexed list, while the even indexed list will remain empty. From a complexity perspective, the algorithm performs very efficiently. It runs in O(n) time because we traverse the list exactly once, and it uses O(1) space as we only allocate memory for a few pointers and dummy nodes. To better understand the algorithm, let's visualize an example with the input list, 1-2-3-4-5. Initially, both odd_dummy and even_dummy are empty. During the first step, we add the node with value 1 to the odd list, resulting in an odd list of 1, while the even list remains empty. Then, we add the node with value 2 to the even list, giving us an even list of 2. Next, we add the node with value 3 to the odd list, which now becomes 1-3, while the even list remains 2. Then, we proceed to add the node with value 4 to the even list, resulting in an even list of 2-4. Finally, we add the node with value 5 to the odd list, making the odd list 1-3-5. At this point, we have processed all the nodes in the input list. The final output consists of the heads of the odd and even lists. The odd list contains 1-3-5, while the even list contains 2-4. Both lists are properly terminated, and we return these results as the final solution to the problem. This solution solves the odd-even linked list problem by rearranging the nodes of the linked list based on their positions, odd and even indices. Here's a step-by-step explanation. 1. Base case handling. The function first checks if the input list is empty, head is none, or has only one node. If either is true, the list is returned as is because no rearrangement is required. 2. Initialization. The odd pointer starts at the head of the list, while even starts at the second node, head.next. The even_head pointer is used to store the starting node of the even indexed sublist so that we can later append it to the end of the odd indexed sublist. 3. Rearranging nodes. A while loop iterates as long as there are more even indexed nodes to process. Inside the loop, the odd pointer's next is set to the node after the even pointer, even.next, effectively skipping over the current even node and linking to the next odd node. The odd pointer is moved one step forward to the newly linked odd node. Similarly, the even pointer's next is set to the node after the newly linked odd node, odd.next, skipping over the current odd node and linking to the next even node. The even pointer is moved forward to the newly linked even node. For connecting sublists, after the loop completes, the odd pointer, which now points to the last node in the odd indexed sublist, is linked to the even_head, the start of the even indexed sublist. 5. Returning the result. The modified list, starting from the original head, is returned as the result. This algorithm runs in O(n) time as it processes each node exactly once, and it uses O(1) space since the rearrangement is done in place without creating new nodes or data structures. Here, we start by defining a solution class for the problem. Within this class, there's a nested static class called listNode, which represents a node in a singly linked list. Each node has two properties, an integer value, val, and a reference to the next node, next. Multiple constructors are provided to initialize the node in different ways. Now, the core of our solution lies in the method odd_even_list, which takes the head of a linked list as input and rearranges it so that all odd indexed nodes are grouped together, followed by all even indexed nodes. First, we handle the base case, checking if the input list is null or has only one node, in which case no rearrangement is needed, and we simply return the head. If the list has more nodes, we initialize two pointers, odd, starting at the head, the first node, and even, starting at the second node. Additionally, we store the head of the even list in even head so we can reconnect it later in the rearranged structure. Next, we use a while loop to process the list as long as there are more even nodes available. Inside the loop, we first connect the current odd node to the next odd index node by pointing odd.next to even.next. Then, we move the odd pointer forward to the newly connected node. Similarly, we connect the current even node to the next even index node by pointing even.next to odd.next, and move the even pointer forward. This alternation ensures that all odd and even nodes are linked separately while maintaining their relative order. Once the loop finishes, all odd nodes are grouped together, and all even nodes form a separate chain. Finally, we attach the even list, starting from even head, to the end of the odd list by setting odd.next to even head. The modified list, now rearranged with odd nodes followed by even nodes, is returned as the result. To solve the odd-even linked list problem, let's start with the example linked list 1, 2, 3, 4, 5. Initially, we set up three pointers, odd, which points to the first node with value 1, even, which points to the second node with value 2, and even_head, which also points to the second node. The purpose of even_head is to ensure we can reconnect the even nodes to the odd nodes later. Now, in the first iteration, we update odd.next to point to even.next, which is the third node with value 3. This effectively skips the second node, and the linked list now looks like 1, 3, 4, 5, none. Then, we move the odd pointer forward to its next node, so it now points to the node with value 3. Similarly, we update even.next to point to odd.next, which is the fourth node with value 4, skipping the third node. This keeps the even list intact. Finally, we move the even pointer forward, so it now points to the node with value 4. At the end of this iteration, the odd and even pointers are ready for the next step. In the second iteration, we repeat the process to rearrange the nodes. First, we update odd.next to point to even.next, which is the fifth node with value 5. This skips the fourth node, and the linked list now looks like 1 3 5 none. We then move the odd pointer forward to its next node, so it now points to the node with value 5. Next, we update even.next to point to odd.next, which is none because there are no more nodes after the fifth node. This effectively terminates the even list, and even is moved forward to none, indicating that we have processed all even nodes. At this point, the odd and even lists are separated, but we need to reconnect them. To do this, we update odd.next to point to even_head, which is the head of the even list starting at node 2. The final reordered linked list is 1 3 5 2 4 none, where all odd indexed nodes appear first, followed by all even indexed nodes. Now, let's look at a shorter example with the linked list 2 1 3. Initially, the odd pointer points to the first node with value 2, the even pointer points to the second node with value 1, and even_head also points to the second node. In the first iteration, we update odd.next to point to even.next, which is the third node with value 3. This skips the second node, and the linked list now looks like 2 3 none. Then, we move the odd pointer forward to its next node, so it now points to the node with value 3. Next, we update even.next to point to odd.next, which is none because there are no more nodes after the third node. This effectively terminates the even list, and even is moved forward to none. To reconnect the lists, we update odd.next to point to even_head, which is the head of the even list starting at node 1. The final reordered linked list is 2 3 1 none. Finally, let's consider an edge case where the input linked list contains only one node, 1. Since there is just one node, there are no even nodes to rearrange, and the list is already in the correct order. Therefore, the output remains 1 none. This demonstrates that the algorithm handles edge cases gracefully, preserving the input structure when no rearrangement is needed. The time complexity of this solution is O(n), where n represents the number of nodes in the linked list. Let's break this down step by step. First, during initialization, we assign pointers such as odd equals head, even equals head.next, and even_head equals even. These are constant time operations, taking O(1). The next key aspect is the while loop, which iterates through the linked list. In each iteration, we perform several constant time operations, updating odd.next to link the next odd node, moving the odd pointer, updating even.next to link the next even node, and moving the even pointer. Each of these steps takes O(1). Since the loop processes every node in the list exactly once, the total number of iterations is proportional to the number of nodes, n. This makes the overall loop operation O(n). Now, after the while loop, we perform one final step, linking the odd list to the even list using odd.next equals even_head. This is a constant time operation, O(1). Summing everything up, the dominant term in our time complexity comes from the traversal of the linked list in the while loop, which takes O(n). All other operations, such as initialization and the final step, are constant time and do not affect the overall complexity. Therefore, the total time complexity of the solution is O(n). Moving on to space complexity, the algorithm uses a constant amount of extra space. We only have 3 pointers odd, even, and even_head to track the current odd node, the current even node, and the head of the even list, respectively. Each of these requires O(1) space. Since we do not use any additional data structures or recursive calls, and the input linked list is modified in place, the space complexity is O(1). Let's analyze the best, average, and worst cases for this solution. In the best case scenario, if the linked list has fewer than 3 nodes, the while loop does not execute at all, and the function completes in constant time, O(1). However, this is just a special case of the broader O(n) complexity. For the average case, given a list with n nodes, the function processes each node exactly once, resulting in O(n) time complexity. Similarly, the worst-case scenario is identical to the average case because the algorithm always traverses the entire list, making the time complexity O(n). When comparing this optimized approach to a naive approach, the brute force method might involve creating separate lists for odd and even nodes, appending to each list, and then merging them. While this naive approach also takes O(n) time to traverse the list, it requires additional space to store the new lists, resulting in O(n) space complexity. In contrast, the optimized solution rearranges nodes in place, avoiding extra data structures, and achieves the same O(n) time complexity with O(1) space complexity. Finally, let's provide a mathematical justification for these complexities. The O(n) time complexity arises because the while loop iterates through each node in the list exactly once, and in each iteration, it performs a constant amount of work. This linear relationship between the number of nodes and the time taken confirms the O(n) complexity. For space complexity, no additional memory is allocated proportional to the input size. The algorithm only uses a fixed number of pointers odd, even, and even underscore head regardless of how large the linked list is. This ensures that the space usage remains constant, which justifies the O(1) space complexity. Together, these analyses highlight the efficiency of the solution both in terms of time and space. When tackling problems like odd-even linked list, there are a few common mistakes to watch out for. First, participants often confuse zero-based and one-based indexing. This can lead to off-by-one errors, particularly when iterating through lists. To avoid this, it's important to carefully read the problem statement to clarify the indexing style and test your logic with simple examples. Another frequent issue is ignoring edge cases. Failing to account for inputs like empty lists or lists with only one or two elements can result in runtime errors. Always make it a habit to explicitly test these edge cases. Additionally, mixing up odd indices and odd values is another source of confusion, especially when the problem description isn't entirely clear. To address this, use descriptive variable names like odd_index or even_value to keep your logic organized. Finally, inefficient implementations, such as nested loops, can lead to timeouts for large inputs. Focus on analyzing the time complexity of your solution and consider using optimized data structures to improve performance. Another pitfall is overcomplicating the solution. Many participants try to use additional data structures or unnecessary computations, which can introduce bugs and make debugging more difficult. The best way to avoid this is to aim for simplicity, break the problem into smaller, manageable steps. On the interview side of things, it's crucial to understand the constraints of the problem. For instance, if the input size is very large, brute force solutions are unlikely to succeed. Recognizing patterns in the problem can also help simplify your approach. For example, many problems involving grouping or separating elements can be efficiently solved using two pointers. Clarity is key during interviews, so take the time to clearly explain your thought process. If you're stuck, discuss the pros and cons of different approaches, like a brute force versus an optimized method. Lastly, always confirm edge case scenarios with your interviewer. For example, ask how to handle an empty list or the maximum input size to ensure your solution is robust. The concepts in odd-even linked list are closely related to several other problems you might encounter. LeetCode problem 328, odd-even linked list, specifically focuses on rearranging a linked list based on odd and even indices. Similarly, LeetCode 905, sort array by parity, deals with separating even and odd values in an array while maintaining their order. LeetCode 922, sort array by parity 2, goes a step further by requiring that even and odd values alternate in the array. Another related problem is LeetCode 86, partition list, which involves partitioning a linked list around a pivot value. These problems share common techniques like reordering elements, partitioning data, and maintaining specific constraints, making them excellent practice for mastering these concepts. There are several approaches you can take when solving problems like odd-even linked list, each with its own trade-offs. A brute force approach is often the simplest to implement and understand, but it's highly inefficient for large inputs due to its O(n²), or worse time complexity. A more efficient method is the two-pointer approach, which operates in O(n) time and is particularly effective for partitioning or rearranging problems. However, it requires careful management of pointers to avoid mistakes. In-place modifications are another option, as they save space by reusing the original data structure. The downside is that they can be harder to debug, especially if the problem has constraints on the order of elements. Finally, using extra data structures like lists or hash maps can simplify implementation and improve code readability, but this comes at the cost of additional space, which might not be allowed in scenarios with strict memory constraints. Choosing the right approach depends on the problem requirements and constraints. Great job completing this challenge. We reviewed an efficient way to reorder linked lists while maintaining optimal time and space complexity. Remember, linked list manipulation is a critical skill for both interviews and real-world applications. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!